Carl, this video is going to be a little bit longer. I tried to shorten it, but I just couldn't figure out a way to make it shorter, so I hope people are going to stick with me. Yes, Carl, I know they don't stick with me on the shorter videos, but I can hope, can't I? Hi! Welcome to episode 6 of Living as Nature, Life versus Entropy. As I hope is clear, these videos are all closely related to one another, each building off the previous ones. This episode follows up on the ideas developed in episode 5, Life on Earth. Here, we're going to take a look at a few fundamental ideas that will help us better understand life. First, we're going to look at the concept of entropy as a law of thermodynamics. Second, we're going to consider the concept of information and its function in relation to life, focusing on the role of DNA in biological information. These two concepts will help us to understand, at least at a surface level, how entropy and life are engaged in a sort of battle, metaphorically speaking, of course. They'll also help us to understand why life, barring some sort of miraculous intervention or some mysterious force of which we are not yet aware, will inevitably lose this battle. Entropy is like Thanos. Inevitable. Except entropy will actually get the job done. Well, I guess Thanos kind of got the job done, but then they went back in time and undid what he did, and I don't know. Anyway, boom. Suck it, movie version Thanos. One broad way to think of the laws of thermodynamics is as a description of the interplay of energy within and between systems. A system is something, or a collection of somethings, with a set boundary. For example, we can think of a cell as a system. We can think of our bodies as systems. We can think of the Earth as a system. We can think of the known universe as a system, and we can think of the entire universe as a system. Oh, the things we can think if only we try. It's Dr. Seuss, Carl. You don't like him? Don't goose the Seuss, Carl. Don't goose the Seuss. Scientists describe systems as open, closed, or isolated. An open system can exchange both energy and matter with its surroundings. For example, human bodies are open systems. We can take in matter, through eating and breathing for example, from our environment, as well as release matter and energy into our environment. For example, bodily fluids and emitting heat. Gross. A closed system can exchange energy, in the form of heat or work, but not matter, or mass. Think of a sealed plastic water bottle in a refrigerator as at least an approximation of a closed system. There's an energy exchange between the water bottle and its surroundings, but you're not seeing much in terms of an exchange of matter. An isolated system doesn't exchange matter or energy with its surroundings. Theoretically, a perfect thermos, which technically doesn't exist, would be an example of an isolated system. I'm just saying, Carl, they're miraculous. They keep the hot things hot and the cold things cold. How do they know? Scientists tend to describe the entire universe, just to be clear, not the observable universe, the entire universe, as an isolated system. Having a sense of these systems, I want to focus on two laws of thermodynamics. The first and the second law. There's a zeroth and a third law, but screw those laws. Yes, Carl, I know they're important and relate to the topic, but I'm trying to simplify here, okay? And explore how these laws help us to understand some broad ideas about the universe, and more specifically about the open systems we call living organisms. The first law of thermodynamics refers to the conservation of energy. It states that energy can't be created or destroyed. Energy can be added or removed from an open or closed system, and energy can be converted between forms within a system, including within an isolated system. So, for instance, chemical energy released from burning coal or natural gases can be converted into electrical energy in the form of a stream of electrons running through wires in our homes. And that electrical energy can then be converted into radiant energy, for example, visible light. And the electromagnetic energy, or radiant energy, from the sun can be transformed into various forms of energy on Earth, including energy that allows creatures to survive through metabolic processes. Mass can also be converted into energy, for example, through nuclear fission or nuclear fusion. But in all of these processes, energy is never created or destroyed. Assuming the universe is in fact an isolated system, it follows that the sum total of energy in the universe at this moment has to be the same as the energy that was in the universe at the moment of the Big Bang, accounting of course for the conversion of mass into energy and vice versa. But that's partly the point. The distribution of energy and the types of energy that exist have changed. And that brings us to the second law of thermodynamics. The second law refers, simply speaking, to the inevitable movement of isolated systems from order to disorder, because energy tends to disperse into less ordered and less usable forms, ultimately leading to equilibrium. By the way, if what I just said makes no sense to you, it's okay. Stay with me. The measure of disorder, or energy dispersion, in a system is referred to as entropy. Entropy is what gives life its irreversibility, and time its directional linear feel, sometimes referred to as the arrow of time, moving from the past to the future through the present. As a side note, there are some really great discussions of entropy out there, and I'm going to put some links in the description if you want to take a deeper dive, or if you find my description unhelpful. Yes, Carl, I know they probably will. But I'm going to offer my description here anyway. If you have a hot cup of coffee and you place it in a 70-degree room, after a while, the coffee will become room temperature, which means that the energy in the coffee has dispersed into the surroundings, in this case, the room, leading to an equilibrium between the coffee and the room. They're now the same temperature. Place an ice cube in the same room, and the energy will transfer from the room into that ice cube, causing it to melt and leaving a puddle of room temperature water. Again, equilibrium. We know that this happens, but why does it happen? The answer is that the dispersion of energy toward equilibrium is so probabilistic that it's practically inevitable. We call this dispersion toward equilibrium disorder because when energy is neatly packed and highly concentrated, it's able to do a lot of work. But when energy is randomly spread out and dispersed, it can't do a lot of work. Energy that's neatly packaged and highly concentrated is referred to as low entropy energy. Energy that's randomly spread out and dispersed is referred to as high entropy energy. Now, there's a spectrum here, but perhaps the form of energy with the highest entropy is heat energy. It's just atoms jiggling about randomly near one another, like when most white people dance. Yes, Carl, me too. This is where I live, right here. This is it. To understand why the dispersion of energy toward equilibrium is so probabilistic that it's practically inevitable, we need to understand the concept of microstates of energy. In a system, there can be various ways the energy in that system can be arranged. Each configuration of energy is referred to as a microstate. When a system is exchanging energy with another system or its surroundings, new microstates become possible because energy can enter that system from its surroundings, which is what happens in the case of the ice cube melting, or energy can leave the system, dispersing into the surroundings, which is what happens when the cup of coffee cools. Now, if we look at all the possible microstates of energy of the cup of coffee in the room, we'll notice that the set of microstates in which entropy decreases, for example, the cup of coffee gets hotter because energy transfers from the room into the cup of coffee, are so improbable that the likelihood of them happening is virtually non-existent. But the set of microstates in which energy moves from the coffee toward the room, thus creating an equilibrium, and a rather disgusting room temperature coffee, are so statistically probable that that outcome is virtually inevitable. To make this point clearer, let's use an analogy involving dice. If you roll one six-sided die, there's an equal chance of each number coming up. No, Carl, I don't care if you know a guy who can get me a dice that always rolls a 6. If you add another six-sided die, now rolling 2, there's still an equal chance of rolling each number on each die. However, there's now a much greater chance of rolling a 7 than there is of rolling a 2 or a 12. That's because the only way to roll a 2 is by rolling 2 1s, and the only way to roll a 12 is by rolling 2 6s. If we think of the arrangement of the dice as microstates, so 1 and 1 would be one microstate, and 6 and 6 would be another microstate, there's only one microstate that results in the macrostate, the overall outcome, of a 2, and one microstate that results in the macrostate of a 12. But there are 6 microstates that result in the outcome of a 7. If you chart the probabilities of outcomes, you'll see that a bell curve forms, with a higher probability of the middling numbers and a lower probability of higher and lower numbers. Now, for the sake of this analogy, we can think of lower and higher numbers as microstates that would lead to lower entropy. For instance, the cup of coffee getting hotter because energy from the room is going into it, or the ice cube getting colder because energy from it is going into the room. And the middle numbers as representing microstates that lead to an increase of entropy, that is, disorder, or the dispersion of energy toward an equilibrium. This maps to reality because the probability toward entropy is greater than its alternative. But you may ask, why does entropy always increase? After all, with rolling 2 dice, there's still some chance of rolling a 2 or a 12. So shouldn't some cups of coffee get hotter and some ice cubes get colder in a 70-degree room? The answer is no, and our dice analogy will help us to understand why. The number of possible microstates in these real-life scenarios is extremely high. And as the number of possible microstates increases, the probability of an equal distribution of energy increases exponentially. This is also true of dice. If you're rolling 2 dice, there's roughly a 16.7% chance that you'll roll a number in the bottom 27% of possible outcomes. In this case, a 2, 3, or 4. and a 44.4% chance that you'll roll a number in the middling outcomes, in this case a 6, 7, or 8. But if we increase the number of dice that we're rolling to 10, there's now only a 2.5% chance that you'll roll a number in the bottom 27% of possible outcomes, in this case anything between a 10 and a 24. And there's a whopping 83.3% chance that you'll roll a number in the middle 27% of outcomes, in this case anything between a 28 and a 42. So you see the likelihood of rolling a middle number increases exponentially the more dice that you add. Similarly, the likelihood of entropy increasing goes up exponentially the more possible microstates there are. And in a situation with the coffee cup or the ice cube, it's more like we're rolling 10,000 dice. With the exponential increase of odds, you are inevitably going to end up with a number representing that middle set. It's a statistical inevitability. In short, entropy increases because of the probability of energy toward equilibrium is so probabilistic, it's essentially inevitable. The second law of thermodynamics tells us that, even if open or closed systems seem to increase in order, disorder in the overall system, in this case the universe, will increase. But it's also true that all systems, whether open, closed, or isolated, have a tendency toward disorder. The reason that open or closed systems can fight against entropy's pull is that they can potentially, at least for a time, take in free energy from their surroundings to sustain themselves against the pull of entropy. This leads to some fascinating things about our universe. First, every time energy is transferred or converted, entropy in the universe overall increases. Second, every system, even open systems, tend toward disorder. If open systems want to resist entropy's pull toward disorder, they have to receive some external help in the form of mass or energy that they can use to sustain themselves. Third, if the universe is an isolated system, entropy will have the final word. The second and third points are important to life, so let's unpack them a bit more. Life forms, as open systems, are constantly contending with entropy. The distinguished environmental philosopher Holmes Rolston III has stated, "Life is an uphill climb against the downhill tug of entropy. Entropy is like gravity, and life is trying to fly." So how does life do it? How do living creatures fight against entropy? In short, the ability to metabolize and maintain homeostasis are essential ways that life contends with entropy. But to do these things, life needs to harvest free energy from its surroundings. And to do this effectively, life needs something immensely important: the ability to encode and decode information. Information is a tricky concept. It seems to be encoded in the universe in the forms of law-like regularity. Think of math or the laws of physics and chemistry. It also seems to exist in local environments in ways that can be read. For instance, to feel temperature and say, "It's getting hot in here, so what? So take a thought." I just want to apologize for that. I don't know what came over me. Is to receive information from a local environment and then convey that information. I feel heat, I say, "It's hot." When it comes to life, information is important in at least 3 ways. First, the information regarding the structure of each individual life form is encoded in that life form's genetic material, contained in their cells. Second, the information regarding how individual components of living organisms function is also encoded in their genetic material. Third, the ability of a life form, or cells within that life form, to receive and decode information from their local environment is essential to their survival in terms of homeostasis and forms of adaptation. For instance, when a doe receives the information that she's hungry, she eats. When she receives the information regarding heat from a forest fire, she runs. And when the right proteins in that doe's cells convey information regarding a shift in the seasons, she'll grow a winter coat. In all of these cases, a very impressive molecule is at work: DNA. DNA is the molecule that carries the genetic information of living organisms. A DNA molecule is made up of a few parts. First, you have 4 nitrogenous base molecules: adenine, guanine, thymine, and cytosine. They're called nitrogenous because nitrogen atoms are fundamental to their makeup. They're called bases because they have the chemical property of being able to form bonds with protons, or hydrogen ions. Uracil is also a nitrogenous base worth mentioning here. It doesn't show up in DNA, but it replaces thymine in RNA structures. These bases can be categorized into 2 groups: purines, adenine and guanine, and pyrimidines, thymine, cytosine, and uracil. These groupings are based on their ring shapes. The bases can join with the sugar phosphate molecule, which includes a deoxyribose sugar and a phosphate, to form a nucleotide. Hey Carl, your face is a nucleotide. That was good. This sugar phosphate forms a backbone for both DNA and RNA. But for RNA, instead of a deoxyribose sugar, you have just your plain ribose sugar. Hence, DNA is deoxyribonucleic acid, and RNA is ribonucleic acid. If you're wondering, the term acid comes from the phosphate aspect of both molecules. Okay, so we have a backbone with 4 bases appearing in a sequence. We just use letters to denote the bases. But if you've seen DNA models, you should be expecting 2 backbones joined together to form that famous double helix. Like this. Each base of DNA only pairs with one other base. Adenine only pairs with thymine. Adenine, adenine, ever loving adenine is taking a chance. They don't like when I sing? Adenine can also pair with uracil and RNA. And guanine only pairs with cytosine. And these pairs form naturally, holding together from hydrogen bonds in the hydrogen from the base molecules. If you recall, we noted in an earlier video that hydrogen, which is one of the primordial elements, plays a key role in the chemistry of life. Here's a prime example. Now we have DNA. So what's up with genes, chromosomes, and a genome? As noted, DNA holds information. It provides a form of communication within cells, a language of sorts. But instructions need to be specialized. Take this action, form this protein, become this cell. So, like a good set of instructions, DNA is organized. I'm going to leave aside for a moment the notion of junk DNA, even though apparently most of what we have is junk DNA. DNA that doesn't seem to do much. The message in the important parts of our DNA is not just stream of consciousness, like when Carl writes philosophy, or, well, anything. We call a strand of DNA that carries specific instructions regarding heredity, the building of proteins, or controlling other strands, genes. We'll discuss the importance of genetics more closely in our video on evolution. We call long strands of DNA, including genes, wrapped up into specific structures, chromosomes. The entire set of an organism's genetic information, meaning all of its genes, is referred to as its genome. The way the genome presents as visible traits, for example, eye color, hair, bone structure, is referred to as an organism's phenome. The number of genes and chromosomes we have don't necessarily map to what we might consider as complexity. For example, humans have 23 pairs of chromosomes, 46 overall. But there are quote-unquote less complex creatures that have more chromosomes and more genes. An African baobab tree has 168 chromosomes, and the Atlas blue butterfly has 448 chromosomes. Genes can function in a number of ways, but one extremely important thing that genes do is provide instructions for protein synthesis, the creation of proteins. Proteins do quite a lot in living organisms, with different proteins fulfilling different roles. They replicate DNA. They transcribe DNA into messenger RNA, which is necessary for the production of more proteins through the process of protein synthesis. They control metabolism, which provides the necessary energy for all of this to work, and a whole lot more. It's like one of those infomercials. But wait, there's more! But in order to do all of this, the right proteins need to be produced to perform the right jobs. And this comes down to information. So how does this information work? It all comes down to the order of the A's, G's, T's, and C's in DNA. Given particular instructions from the DNA itself, proteins will copy lengths of DNA. Genes. That copy becomes known as messenger RNA, and it goes out into the cytoplasm of the cell to be read by ribosomes. The ribosomes read the codes of letters in sets of 3, which are called codons. Codons specify amino acids. So codons add amino acids to a chain in a specific order. The right ordering of amino acids creates a specific protein that can do a specific role. And all this comes down to information, the language within cells that begins with genetic code. One crucial role that proteins play is in metabolism. When creatures like us eat and drink, allowing the cells in our body to metabolize energy from our environment through cellular respiration, we're providing energy to ourselves. Or rather, our cells are providing energy to us. And proteins are necessary for this process. Which of course means that information is necessary to this process. And it is just these sorts of processes, protein synthesis, metabolism, and the resulting homeostasis, that allow open systems like living organisms to battle against entropy. But there's a catch. See, the infomercials never tell you about the catch, Carl. I'm gonna tell you about the catch. In fighting entropy in our own bodies, we actually increase entropy dramatically in the universe. David Christian refers to this as entropy's complexity tax. This comes back to that second law of thermodynamics. Anytime energy is transferred or converted, entropy increases in the overall system. This is because no process is perfectly efficient in converting or transferring energy. Something is always lost or wasted. By the way, this is why a perpetual motion machine is impossible. So those social media ads are disinformation. To explain what I mean by wasted, let me use a real-life example. Think about our sun. It's an open system. It receives mass and energy from its surroundings. It also releases mass and energy into its surroundings. Like other stars, our sun is engaged in nuclear fusion, fusing hydrogen into helium. So it's on the main sequence, which we talked about in a previous video. This activity releases a tremendous amount of energy. But more importantly for us, it produces low entropy energy. Energy that is ordered, highly concentrated, and able to do work. This low entropy energy comes to Earth in the form of high-frequency photons, visible light, which are cast out from the sun into surrounding space. Now, this light reaches the Earth, and a green plant gets a hold of those tasty high-energy photons and uses it to convert water into O2, producing ATP and NADPH, molecules that can store energy, and ultimately producing sugar in the Calvin cycle. In other words, it engages in photosynthesis. The photosynthetic process is amazing, but it's not wholly efficient. A lot of the sunlight's energy is lost in the conversion process, including through the production of heat. And you'll recall that heat is a very high entropy form of energy. It's scattered, dispersed, and can't do a lot of work. Here, the overall entropy of the system increases, even as the open system, the plant, is maintaining its order and stability through metabolic processes in its cells. Now, let's say a cow comes along and finds our friendly plant. He's hungry, so he gobbles it up. The cow goes through a process of digesting the plant, breaking it down and getting some carbohydrates from it, which can be used by the cow's cells to synthesize ATP. Think of ATP as the batteries of life, or just a battery pack for cells. But again, energy is lost in the process, and again, some of it is lost as heat. Cows emanate heat, you know, Carl. Finally, you come along and you're looking for a steak dinner. I don't like where this is going, Carl. So you eat the cow. I just feel bad for the cow. You know, I'm not crying, you're crying. Your mom is crying. Now you get some ATP through similar processes as the cow. But again, there's energy loss in that process. Heat. Furthermore, as the plant, the cow, and you use the energy you gain to do work, you convert that energy into less ordered energy. Again, think heat. In this sense, every process, even those processes that maintain order and structure in an open system and seem to keep entropy at bay, ultimately increase entropy overall because they convert low entropy energy into high entropy energy, heat. In fact, living creatures are immensely efficient at increasing entropy in the universe. For these reasons, in the end, from the perspective of our natural world, entropy will have the final word. Every ordered structure will fall into disorder. Every living organism will die. And ultimately, the entire universe will reach maximum entropy in a sort of death of its own. Well, I think that's a good place to leave it for today. Keep fighting the good fight, and simultaneously losing the good fight as you do it. Until next time, farewell.